All right, so example number 1 for Francis turbine. Let's read the, the question. A reaction turbine works at 450 RPM under a head of 120 meters. Its diameter at inlet is 1.2 meter and the flow area is 0.4 meter squared. The angles made by absolute and relative velocities at inlet are 20 degrees and 60 degrees respectively. With the tangential velocity, determine the volume flow rate, the power developed, and the hydraulic efficiency. So this is a reaction turbine, and as usual, we try to list down information that we can grab from question that will help us in solving this question. Okay, so first of all, from the question, we know that we know that the speed of turbine is given in the question is 450 RPM and the head is 120 meters and the diameter at inlet D1, or you can use DI or whatever notation that you like, is equal to 1.2 meters, and flow area, which can be calculated by pi d1 b1, is equal to 0.4 meter squared, and the angle made by the relative velocity at inlet is theta equals 60 degrees, and angle made by absolute velocity alpha is equal to 20 degrees. So these are informations that we can extract from question, and in order to solve turbine question, usually and most probably we need every time we need to sketch the velocity triangles. Okay, so please do sketch the velocity triangle. Okay, we look at first the velocity triangle at the inlet of the vane. Okay, so this is the vane, okay, and this is the inlet where water came in, go into the vane of the turbine, and this is the outlet. Okay, so the absolute velocity going into the vane v1 is given by this line. Okay, this is the absolute velocity of the water. Okay, and then wait a minute, Sarah and Khadijah main kat luar. Okay, and then at the same time, the vane or the turbine is moving with velocity u1 given by this arrow. Okay, and at the velocity that is filled by the vane is actually v_r1, okay, the relative velocity. Okay, so v1 is the absolute velocity of the water jet. u1 is the velocity of the vane. And because we have two velocities here, so um, the velocity that actually filled by the vane is the relative velocity. Okay, so VR1. Okay, and from this triangle we can get the um, vertical components of the absolute velocity of the water as VF1, and the horizontal component as VW1. Okay, and the angle made between V1 and U1 is alpha. Okay, alpha, which also known as the angle of blade. Okay, angle of blade. And the angle between VR1 and U1, or the direction of motion, is theta, is equal to 60 degrees. Okay, so now we have completed the velocity triangle at the inlet. And we move on to the velocity triangle at the outlet. Okay, so we have velocity VR2 exiting the vane in this direction. Okay, and now U2, the velocity of the vane is in direction, is given by this arrow, and you can see clearly here that U2 is large than U1 because the vane got energy from the jet, okay, from the water, which transfer into velocity, transfer into kinetic energy that move the vane faster than before. Okay, and then we have the absolute velocity, v2, given by this um, arrow here. Okay, and in this case, because the water exit the vane axially, so beta 2, or beta in this notation, is equal to 0, which means v2 is equal to vf2. Okay, if the angle at the exit is equal to 90 degrees, then v2 is equal to vf2. Okay, and vw2, which is the uh, horizontal component of v2, is 0 because v2 is in straight y axis, okay, or z axis. Okay, so v2 don't have any vertical component, it's only have no, don't have any horizontal component, only vertical value. Okay, so now we know our uh, velocity triangle at the inlet and velocity triangle at the outlet, and also we have list down all information that are extracted from the question. Okay, so next we want to solve the first question, which is the volume flow rate. Okay, we know volume flow rate can be calculated by this equation, which is pi d1 b1 is the area at the inlet multiplied by the velocity at the inlet. Okay, so we have the area at the inlet given in the question, but we don't have the information about VF1. Okay, before we move further, let's have this velocity triangle at the inlet as our reference here. So we want to calculate VF1. VF1 is actually the vertical component of um, V1 or the absolute velocity. Okay, so we can calculate VF1 from this um, relationship. Okay, tan alpha equal VF1 over VW1. Okay, so we know alpha value is 20 degrees, so we just write down tan 20 degrees equal VF1 over VW1. So we don't know VW1 yet, so but we can write VF1 in terms of VW1 here, which is equal 0 0.364 VW1. Okay, and we mark this equation as equation 1. Okay, moving on. We also know that tangent theta is equal to VF1 over VW1 minus U1. Okay, VF1 here, wait, okay, tangent theta is equal VF1 over this length, okay, which can be calculated by VW1 minus U1. So we get this expression. Okay, so we have VF1 equal 0.364 VW1 here, and we plug in into this equation, and VW1 VW1 minus U1 is actually we need to calculate U1. We need to calculate U1 first. Okay, so U1 in this, even though it's written here straight away, but we don't know U1 yet. Okay, so in order to calculate U1, we can use this relationship. U1 is equal to pi d1n over 60. Okay, the rotational the RPM here, 60 RPM. Okay, so from this relationship, we know d1, we know n, the RPM, sorry, and we can get u1 equal 28.27 meter per second, and we plug in into this equation. Okay, so next, so we already have VF1, not yet. And now we can calculate VW1 in order to get VF1. Okay, so tangent 60 degrees equals 0.364 VW1 over VW1 minus U, or 28.27. So we know tangent 60 degrees is equal 1.732, and then we plug in the value here. We plug in the value here, equal to this expression, and we rearrange this equation so that we can get V1 equal to 48.96 over 1.732 minus 0.364. And finally, we get VW1 is equal to 35.79 meter per second. And from equation 1, now we can calculate VF1, which is equal to VW1 uh, 0.364 multiplied by VW1, which is 35.79. And we get the value of VF1 is equal to 13.027 meter per second. Now we can calculate the volume flow rate by plug in the flow rate that is given in the question and VF1 that we just calculated, and we get the volume flow rate as 5.211 meter cube per second. Okay. So next is power developed by the runner. Okay, power developed by the runner can be calculated using this equation that if you watch my previous video, you know this where this equation came from. Okay, so rho Q VW1 U1, what we do before we go further, it's good to have this reference because it's supposed to have plus minus VW2 U2 here, right? But because VW2 is equal to 0, then we can cancel out this term. VW2 equal to 0 because beta is equal to 90 degrees. Okay, so we end up with only this equation. Now we just plug in the value that all this value we already know. Rho is the rho of water, the density of water. Q the volume flow rate. VW1 we have calculated, and U1 also we have calculated previously. And we got the power developed is equal to 5272402 Newton meter per second, or you can calculate in kilowatt by divide with 1000. You can get a value in kilowatt. Okay, and then finally we want to calculate the hydraulic efficiency. So hydraulic efficiency in this case can be calculated using this equation. VW1 multiplied by U1 over GH. So all these values is we already know. So we just plug in the values and we get the efficiency, or the hydraulic efficiency of this turbine is equal to 85.95%. Okay, so this is example number 1, how we solve this question step by step. Okay. Okay, so in an inward flow reaction turbine, the head of the turbine is 32 meters. The external and internal diameters are 1.44 meters and 0.72 meters respectively. The velocity of flow through the runner is constant and equal to 3 meters per second. the guide blade angle is 10 degrees and the runner vanes are rigid at inlet. The discharge at outlet is radial. Determine number 1, the speed of the turbine. Number 2, the vane angle at outlet of the runner. And number 3, hydraulic efficiency. As usual, our practice is first extract as much information as you can from the question. Okay, so we list down from the question. We know that the head on the turbine is 32 meters. The external diameter is equal to 1.44 and the internal diameter is equal to 0.72 meters. And the velocity of the flow at the inlet and outlet is constant. So instead of VF1, VF2, we can just simply put the velocity of flow as VF because it's constant, equal to 3 meters per second. And the guide blade alpha equal to 10 degrees. And the runner vanes are radial at inlet, which means if radial means the theta is equal to 90 degrees. So 90 degrees mean no horizontal component of the absolute velocity. Okay, so wait a minute. So VW1 equal to U1. And same, the discharge is radial. So the angle at outlet is also 90 degrees. So we know VW2 and V2 equal VF2, which equal to 3 meters per second. So this is information that we can get or we can extract from the question. And then we sketch the velocity triangles at the inlet and outlet. And remember, it is essential for you to draw these velocity triangles by drawing the vane and the velocity triangle at the inlet and draw or sketch the velocity triangle at the outlet of the vane. Okay, this is, even though it's not stated in question, but this will show your understanding of the question. Okay, so first draw the vane. Okay, and then draw the velocity triangle at the inlet, and then draw the velocity triangle at the outlet, and also all the notation, for example V1, alpha, theta, because you're going to use this all information when you solve your problem. If you don't write down where is alpha, for example, where is theta, where is beta, when you use that term in your answer, then I don't know which. For example, you write cosine alpha, but I don't know alpha is referring to which angle. Okay, so make sure you draw or you sketch the velocity triangles properly before you solve problem regarding turbine. Okay, and draw your velocity triangles in one diagram. Okay, I don't want you to just draw the inlet at some other place and outlet velocity triangle at some other place. Okay, draw the vane and sketch the velocity triangle at the inlet and then sketch the velocity triangle at the outlet. Okay, that is how we practice. Okay, so first all this information and then draw the velocity triangle. Okay, next we try to solve the first question. Okay, the first questions want to ask about the speed of the turbine or N. So we start by writing down the equation to calculate N. Then from there, we know what information that we have and what information that we still don't have that we need to calculate. Okay, that is how the flow of thinking. Okay, if you look into the solution given by books, it's not a good way to explain the flow of thinking, because they know what information that need to be calculated already. But to show the flow of thinking and how you solve the problem, uh, it is by first writing down what equation that can be used to calculate the specific parameters that been asked in the question. Okay, for example, in this question, the speed of the turbine. So write down the speed of the turbine can be calculated using this expression, n equals 60 u1 over pi d1. This expression is given, is a common expression for Francis turbine or for turbine. Okay, so from here we know that we we have the information uh, pi at d1, but we don't have u1. So we know um, okay, so look into the velocity triangle. Um, so we know that u1 is equal vw1. All right, so and we from velocity triangle, in order to get u1, we can use um, the relationship of tangent alpha, okay, which is equal to vf1 over u1, okay, and we rearrange this expression to get u1 equal vf1 over tangent alpha. Okay, we know vf1 or equal to vf is constant, and it's given in the question equal to 3 meter per second, and over tangent 10 degrees. Alpha is also given in the question as 10 degrees. Okay, alpha is the guide blade angle. So from here we can get the value of u1. Okay, we get the value of u1 by solving this expression, which is u1 equals 17.01 meter per second. And then we can calculate the speed of turbine because we know u1 from what we have calculated here, and d1 is given in the question. All right, so you got the speed of turbine as 225.6 rpm, or rotation per minute. Okay, this is the flow of thinking that you have to have in order to solve this kind of problem. Okay, start with the expression or the equation that can be used to directly solve the problem, or to directly get the what the question want. And then from the expression from the expression or from the equation, we know what information we have, and we have to find the information that we don't have, okay, by using another expression. Okay, and then we write down that expression to calculate the needed information to solve the intended equation. Okay, so now we look into next the hydraulic efficiency, or before that we're supposed to calculate the It's fine. We calculate the hydraulic efficiency. Okay, the hydraulic efficiency, write down the the expression or the equation that we can use to calculate hydraulic efficiency. In this case, this is the expression. Okay, so from this, we know that which information that we have and what information that we don't have. Okay, in this case, we have VW1 and we have U1 that calculated before this, and we have the head given in the question. So we plug in the information or the values in the equation, and we will get the hydraulic efficiency is equal to 92.17%. Okay, VW1 is equal to, if you look here, VW1 is equal to U1 because it's radial. Okay, we look back into this um, to this triangle. So VW1 is equal to U1. Okay. Before we calculate the hydraulic efficiency, this is the we're supposed to calculate the vane angle at the outlet first. Okay. In order to calculate the vane angle at the outlet, it, we we have this velocity triangle at the outlet as our reference. So we can use, we want to know this particular angle. So we try to write down the relationship that we can get from velocity triangle to calculate phi. Okay, so we know phi from velocity triangle. Phi is equal this arrow over this arrow. Okay, or specifically V2 or VF over U2. Okay, then we don't have the information of V2 U2. We already have VF equal to 3 seconds, but we don't have U2. So we calculate U2 using this expression. Okay, in this expression, phi is known, V2 is given, and N is given as well. Or no, we calculated N before this in question 1. Okay, so we can get U2 by plug in these values into this equation, and we will get U2 equal to 8.505 meter per second. So next, we can calculate phi using the triangle relationship here, the trigonometry here. So we have VF2 equal to 3 and U2 is equal to 8.505, and we get tangent phi equal to 0.3527. So in order to get the value of phi, we just inverse the tangent. We get phi equal to 19.43 degrees. Okay, so we have solved this example number 2. We have calculated the first one is, what is it? The first one is the speed of the turbine, and then the vane angle at outlet of the runner or the phi, and the hydraulic efficiency of the turbine.